Hello, my name is Habib. I'm a data scientist at Wolt. Almost exactly a year ago, I joined Wolt, and I work on the logistics team. More specifically, I work with what we call assignment, which is one of the logistics engines that we have at Wolt. So what I'm going to talk about today is more on the logistics side. So how we do logistics at Wolt and how it's empowered with like a lot of machine learning models and how we improve those models as we go. So this is the agenda, or this is what we're going to talk in. So let's start directly with logistics. So we had a little bit of presentation from Leonard about Wolt, so I'm not going to go a lot into that, but basically our vision is to be a platform where you can have the whole city delivered within minutes. It started in 2014 with restaurants in Helsinki, but now it's empowering deliveries of all kinds, from restaurants, grocery, pharmaceutical, cosmetics, etc. And it exists in a lot of countries. We're at 27 countries, more than 500 cities. And all of this will not be possible without having three main apps, basically, that we use. You have the customer app, which is what you as a customer, someone who wants to get a food delivery, sometimes delivered to their home, use. Then you have the courier partner app, which is what courier partners use then to get delivery from point A to point B. And the merchant app, which is how we're empowering the venues. So those are the, or this is like the building blocks of Wolt, and the logistic platform is basically what's empowering those three to synchronize. So logistics is a bit of an enabler in that sense. On one hand, from a logistics eyes, what we care about when it comes to customers is that every time they order something on Wolt, we want that to be a delightful experience, in the sense that if we promise you a delivery time, we want to keep that promise. And that basically, by having that promise kept, we're showing our quality of service, but we're also getting loyalty from our customers. So we want them maybe to come back, order again, and expect the same quality of service. So it's as simple as that. Logistics is a game of time and keeping time. Talking always about time when it comes to merchants, which are restaurants, grocery, it's the same thing. We want to enable or facilitate the operations. So once we have an order on the platform, we want to communicate to the merchant the exact time when that order is going to be picked up. Simple as that. And then you have the courier partners who have their own vehicles, specific locations, etc. So we want to give them at any given time the best possible delivery. And logistics is basically what connects all three. What you see as a customer when you open the app is basically this. You come in into discovery page, you see a lot of venues, and you see those numbers at the bottom of each venue. This is basically what we promise you will be the expected delivery time if you order from that specific venue. Once you choose a venue, then we know maybe you're looking into this, we give you another estimate, which you see here. After that, you place an order, we give you tracking experience. So you can see at any time if something happened with your order, for a reason it got delayed or for a reason it got even speed up, you will see it here. And then your delivery is over, and then you get whatever you ordered, be it food, grocery, whatever. So that's what you see as a customer. And as the logistics teams, we're working on giving you a promise and fulfilling that promise. So what happens while you wait for your order? Again, it all starts with placing an order. At that exact moment, once the order is sent, we're already trying to find you someone who can deliver it. We also send that order to the venue, that can be a restaurant, a grocery shop, to start preparing it. So you have an order preparation. Once we have someone who can pick up the order to our platform, the pickup starts, and then they fulfill the pickup. So that means they go to a venue, and at the venue they can be a little bit early, a little bit late, or just on time. They mark the pickup as completed, then they need some time to start doing the drop-off. Drop-off starts and then finishes. So nothing too complex, but you really have to get all these moments right in the delivery timeline. So this is a bit the simplification of the process. Now I'm going to go a little bit more into the detail of each step. And where we're going to start is what we call pre-estimates or pre-checkout delivery estimates. And those are basically the things you see before you place your order. So you see them either at a venue level or at like landing page level. And those are really important for us because this is the first time a customer sees what time can we promise them to provide our service in. And that means two things. It's a fight between earliness and lateness. You don't want to provide, if you give ETAs that are too high, customers maybe will not order because again, what is taking too long with this? If the delivery estimate is over an hour and you're super hungry and you want food, maybe you're not going to order. And that's costly both for our customers, but also for us. Like we're missing an opportunity, and the customer, maybe if we're wrong with these estimates, just missed an opportunity to order from somewhere they wanted to order. And the only reason they didn't do that maybe is the excessive delivery time. So earliness is dangerous in that sense. And lateness, if you have an ETA that is too low, so you promise something that you can keep, and then it becomes too late, customers will start wondering where is the food or where is the grocery. And usually that means you need to contact support, and support actually means also it's a quality of service cost. We're not providing the service we promise, but also someone actually needs to go in, a human resource needs to go in, look what went wrong, and help the customer. So we can't promise too early. So we just need, at any situation, get the right time, basically. So that's why this estimation is really, really important. But it's also very complex. And the reason for this complexity is threefold. Like, first of all, it's just the scale we operate at. We are 27 countries, more than 500 cities. They're all different in many ways. Topography in Stockholm is not the same as in Georgia. Weather in Athens is not the same as in Stockholm. If it rains in Athens, maybe that will affect traffic a little bit more than it will affect in somewhere where it rains all the time. So all of those things make it a little bit complex, right? Then you also have the variety we have in terms of merchants on our platform. Delivery time of off-the-shelf ice cream is not the same delivery time as a very well-cooked dish from a top restaurant. So all of those things you have to take into account, but also the users, where do they live, how far they are they, etc. And the other thing is on courier partners. There can be differences between how courier partners are in one country versus another, what kind of vehicles they have, what speeds they drive in, etc. And last, it's just the diversity in the merchant again, which translates in just big differences when it comes to how long it will take. Like, is the order one item? Is it 10 items? How much it will take? A supermarket order is not always too long. So if you're just buying bread and something, that might be super fast. But if you're buying 10 items, that might be too long. If you have to order 1 kilo of something, it's all these variations that we have to take into account. So how do we approach this? We go for one model to roll everything. So in the pre-checkout, so before you place an order, the number you see is basically predicted to tell you how much it will take from the moment you click on I want to order this to the moment it's at your door. So we predict end-to-end delivery time. And for that, we use a couple features, but we can categorize them into specific categories. I'm giving examples here. Or specific information. So that can be the distance between where the order is placed to your domicile. Then we look at venue-specific information. So is that a restaurant, etc. But one specific feature here, for example, is we look at, in general, what is the average fulfillment time for that venue in that city, in that country. And then you have city-specific or city-state-specific features. So we look, for example, into the supply-demand situation. Are there too many orders for too little couriers, or is it the other way around? What is the average preparation time in the last 30 minutes? Because that can give us an idea if something is going on in the city, like a traffic jam or situations like that. We look at the past mount data on pickup estimates. And something you could have guessed easily, like weather conditions. So those are the kind of features we have here in this model. And the modeling approach that we had for this was very simple. We used a tree-based model, more specifically an XGBoost, which is, again, a tree-based modeling technique. For categorical data, and we have a lot of categorical data, we use a simple target encoding, which basically takes the average for that category, the average on the target variable for that category. And we use an MSE loss. So pretty simple, really simple architecture for people who work within data science and the machine learning modeling in general. But we also wonder if this is the right approach. And the reason why you use tree-based modeling is on tabular data, there's a lot of literature that says this is much better than deep learning, right? And we started looking at that literature. So we just give you an example here where this article, for example, once you look into the detail, for example, you look at all the data sets that are used in this article, for example, are maximum 50K samples. And for categorical variables, the cardinality was at max 20. And again, I'll go back to the Wolt scale. And for Wolt scale, if you just look at merchants, which will be then a categorical variable here, we have over 150,000 merchants. So we need to question all those assumptions that we made. And that's when we started looking at new types of architecture. So you might have guessed it already. We went into the deep learning approach, or deep neural networks approach. And what we used there is Tosh. We use Lightning, which is a classic way of doing deep neural networks. We use embeddings for categorical data, which is a little bit more advanced, a little bit more sophisticated, and works well with deep neural networks. And Huber loss as a loss function, which smooths a little bit the mean absolute error that one could use as well. So we looked at this approach, and using PyTorch actually made the things speed up a little bit. So I think a couple of weeks of work, we have a model and tested it. And then we saw that the accuracy for pre-estimates actually increased by over 6% using the NN-based model. In this particular test, we used a simple A/B test. But at the end, I will come back to this because A/B tests actually are not the way we usually do our tests in logistics. But anyway, that's how we got this number, the relative increase. So just some learnings, since we're in a data science context. Some of the learnings from the team, at least on the using Torch. It's really well when you it helps a lot with the organization of the code. And this is quite important since we're growing massively, or we have grown massively on the last years. That makes just things easier to work in a team. It's fully integrated, or the integration with the MLflow is free. And then a couple, things that are very nice with PyTorch is you have those metrics. You can include your custom metrics, early stopping of learning, and learning rate tuner that you have on just by using PyTorch. So this is quite a nice thing for at least our team members who work mostly with PyTorch. And our MLOps stack is pretty simple as well. This is how we usually do with our models. We will plan for some new modeling technique, develop the model, develop it, and then repeat, and then evaluate and repeat. So this is a very simple approach that I think is quite standard. We use Flight for our model retraining. We use MLflow for tracking models, and we use Sildan Core for serving models at scale. So yeah, it's pretty simple. So this is just one model that we use in logistics. So this is what happens before you order, right? We're giving you a promise. That promise comes basically from this model. Now I'm going to go to how do we fulfill that order. And even there, we have a couple of models that are doing estimation as your order is being delivered. So why do this matter, actually? I'm going to take it from the venue's perspective and not from the customer's perspective, just to show why this is important. Once an order is placed, we send it to a merchant and we give them a pickup time. And we agree on that pickup time with that merchant. Now, once there's a courier partner who goes for picking up this order, there are three options, or there are three scenarios. They arrive exactly at the moment that we estimated. Then perfect handshake, they go in, get the pizza, all is good. But there are two other scenarios that you can guess easily. The courier partner arrives late. In that case, a lot of people are going to be unhappy, sorry. The food is going to wait. So that means cold the food. That affects our quality of service. That is not something merchants want, and that is not something the customers want. They will get the cold food, they have to wait longer, etc. If we arrive too early, the courier has to wait, and the task can be actually taken longer. So we might have estimated a little bit too aggressively. So those are the three scenarios from what happens at the merchant. At the customer, you can just think like, if you're given the wrong times, things arrive later. And that means people are not really happy with that. So how does the fulfillment look like, or how is it decomposed? So it's dissected basically in those three things. We have the pickup fulfillment, which is basically courier partner starts going to pick up the order. They arrive at the venue, and then there might be a wait time, there might not be a wait time. It depends on how the whole thing is going. After that, they will start a drop-off, and then they will do the drop-off fulfillment. The pickup fulfillment is in itself then dissected into two parts. The travel time, so you travel from point A to point B. Point A being where you accepted that order, because courier partners can reject orders as well, to the point where they're going to pick it up. Once they arrive there, there's a service time, which means I need to park my vehicle, I need to go into the restaurant, I need maybe to look around where the restaurant is, pick it up, put it into my bag. And there can be some wait time there as well. Maybe I arrived on time, but the food is not ready. Same with the drop-off. You'll have to travel from the venue where you picked up grocery food to the customer, and that the customer is the same process. You have to park your vehicle, knock on the door, call, go upstairs, anything can happen. So this is basically how it's decomposed. And for each of those 4 moments where you have time, pickup times, travel time, both a drop-off and pickup, have also their own machine learning models that predict them. And those are used basically also in the task allocation algorithm. And the task allocation is basically how to decide which courier partners are best for executing a delivery. So what we have is basically simple. We have a set of deliveries, pickups, and that consists of pickups and drop-offs. Some online courier partners. We have the location, what vehicles they have, and then we have the service times. We have our ML services that give us a service time prediction and the travel time prediction. For fulfillment estimate, we then feed all of this into our vehicle routing problem solver, which does the task allocation, and that gives us another list of tasks that couriers then receive. And once we have a courier partner for each order or for an order, we can also track or give you an estimate of how much time is left for your order to be delivered. So those are really, really important, not only because we promise stuff, but it's also what actually makes the allocation happen. So I'm gonna first look at the travel times. It's fairly simple, actually. We have a huge scale again, but we use mainly OSRM maps, which is a map service, to actually get a value of travel time. So we just feed it like geolocations, and then we can get a travel time. But we also rely on other third-party map providers that maybe can be better for some contexts or from some countries. So OSRM is quite good in average, but in some countries, maybe maps are much better from our third party. So it's a mix, and sometimes we look into which one is better. We analyze that and then decide which one we go for. And once you get from OSRM, you get a prediction. So we will have to adjust that prediction, because what happens there is you have a kind of speed that gives you then a time. So from point A to point B, given that speed, how much time it will take. But it's agnostic to what kind of vehicle you have. So that part we need to fix ourselves. And that is an ML model that then calculates this thing we call traffic multiplier. So it becomes this very simple formula. We get a travel time estimate from OSRM. We multiply it by a traffic multiplier. The traffic multiplier comes from an ML model that we train on previous data, etc. And then it gives us a corrected travel time that takes into account basically the vehicle type that couriers have. So it's as simple as this. And that gives us basically the travel times estimation. Then the second leg is the service time. And this is also another machine learning model. And then I'm going to go fast into what it represents. So it's basically once you arrive into a geofence. So that's like an area around wherever you go in, pick up or drop off, so merchant or customer. And we want to capture how much time it will take you to find a parking, to walk to the venue, to find the entrance, etc., etc. For this, our current modeling technique is also XGBoost. We have two models, one for the pickup and one for the drop-off, mainly because you would assume there's the differences between pickup and drop-off. Pickups usually are in areas with a lot of restaurants, shopping malls, etc. While drop-offs, you're more in residential areas. And that can be different, if you deliver food in Tokyo, you have skyscrapers. If you deliver food in Stockholm, what's the right word? But it's merely flat compared to Tokyo. So here we have, maybe Stockholm was not the, let's say Linköping, everything is flat. So those models take into account a couple features that you can also get, like what kind of vehicle type you have. Cars maybe take longer parking time, while maybe bikes don't. Order size, order size maybe takes longer time to pick up. You need to check if everything is there before you take it to a customer, because you want to forget something at the restaurant. And we look at other features that usually are used in general machine learning modeling. So here we look at the average service time for a given venue in that neighborhood. So we differentiate maybe venues that are in busy neighborhoods versus venues that are in neighborhoods that maybe have lower demand. You would just assume the preparation there can be different, right? And the stack, our MLOps stack is fairly similar. So we use MLflow, Silicon Core, and Interlight. Now I get to the last part of this presentation where I want to emphasize a little bit of how we do experimentation to improve these models. And the reason why we wanted to present this is basically when you look at this, it's like, oh, it's all that simple. The classic machine learning modeling, you have a problem, you throw data at it, you try XGBoost, it works fine. You're like, oh, let's do neural networks. It works better. Everybody's happy. But it's not that simple. I'm not saying that is actually simple. That is quite complex, but it's even more complex. In our case, what we really have to care about a lot is, I'm going to focus on this. There are other things that can increase complexity, but the network effects. And that is basically simple. There's no delivery that happens in isolation from other deliveries. So if delivery to one customer depends heavily on how it's going for other deliveries. So if we predicted wrongly, and then you're taking longer time on one delivery, that affects the next one, that maybe affects the allocation to the other deliveries. Maybe we're gonna get something. So all of that plays heavily, which means that every time we build a new machine learning model, a new algorithm, we need to understand how it actually impacts things. If you do A/B testing, you can't really isolate to group A and group B, because there's the problems of independence that ruins basically any kind of scientific approach you want to do to this. So what we usually do is switchback experiments, where I'm going to go a little bit more into details, but basically instead of randomizing on delivery level, you're randomizing more on time. and on location. And I'll explain this a little bit better. So in A/B tests, let's say you have this as a single delivery. You have a control group where you don't change anything. You have a treatment group where you want to apply a new algorithm, let's say, or a new machine learning model. You will do this, right? Assuming there's no spillover effects, there's no network effects, this works fine. But when this does not work, you need to randomize differently. And the way you do that in switchbacks is basically having those, what we call buckets of region and times. So same deliveries, just this time we will look into which locations are they coming from and which time, at what time. So this is just a graphic example, but let's say those like dashed line you see here is basically time stamps, and then the horizontal ones are basically locations. So the top row is one locations, middle row is a second location, and the third location is totally different from each other. So what we will do here now is you will decide for each bucket, do I do a treatment or do I do a control? So if it's a treatment, so if it's a control, I just leave it as it is. If it's a treatment, then I will activate another machine learning model. And then I will get data from those buckets. So a little bit more advanced, I'm going to give, this is not really advanced, but I'm going to give a little bit more different graphical representation with a little bit of the challenges that come with switchback as well. So let's say we have two machine learning algorithms. We want to test the current one versus the new one. We decide to test it in 3 regions. How it will work basically is we will split those regions, or we will have a system that can activate and deactivate the new algorithm. So when you activate it, then we're treating that, we're seeing the effect of that treatment. When it's deactivated, then it's like back as it used before. For that, you will have a switch point with the switch probability. So how often, or what's the probability of switching from a variant to another one? That's basically what it is. And then we have switching intervals, which means how long do we keep one variant active at a time. So let's say here at 11 o'clock, we have a switch point. So at 12 o'clock, we have a switch point. And basically, you throw a coin, and then you get like either a control or a treatment for the next hour. So in that case, in region 1, we set control, region 2, we set control, region 3, we get treatment. So at this, in region 2, for the duration of 1 hour, we will have the new algorithm activated. And you will do that basically every hour. And it's totally arbitrary. Right. Now, this is all fine, but there are problems even with this. And the biggest problem that you need to take also into in any experimental design is the carryover effect. The carryover effect basically is when you activate a variant, at the end of the hour, you switch to the other variant, the effects of the previous variants still persist even after you switched. So let's say you have a model that underestimated some metric. That effect of underestimation can be still persistent because there are some deliveries maybe that started before you did the switch that are gonna be ending in the next phase. So that for that you need to have what we call a carryover period, which is basically how much time do you need before the impacts from the previous variants do not persist to the next hour. And I'm gonna give examples. So if we look at that little dashed line, in this case, we had in region 3, we had control at 3 o'clock. At 4 o'clock, we switched to treatment, but that data in that hour will actually be dismissed because we're still living the impacts of what happened in the previous hour. But after 1 hour, we assume that everything now is being allocated or being calculated to the new algorithm. This data then is used. And this is basically happens every time we switch variants. So the challenge here with this design is, well, you get rid of the problems of independence that you had before between your samples. You have a randomization that works, but it's usually more complex. Like there's a lot of like thinking that needs to be done beyond statistical power calculations, and the statistical power for this is very low. Because if I go back to the previous slide, there's a lot of data you dismiss. So because of the switching. But also on the terms of analysis, I recommend a really nice article that is done by a equivalent team at DoorDash, our parent company. on the rigorous, on how to make rigorous switchback analysis. So even on how you do switchback analysis, you can actually lose data by certain aggregations that you need to do in order to maintain all the independence hypotheses that you have, and the lost data. So that's the challenge with this setup, but it gives you a proper idea of how, any improvement you do to your logistic system, be it an email model, be it something in the algorithm allocation, especially when you have network effects, gives you a rigorous analysis. So yeah, to recap, we went to our logistic, basically how we do ML in logistics, and how we do AI in logistics in general, from the pre-checkout delivery estimates, a little bit in details, then the fulfillment, and how we use switchbacks to keep improving. That's it actually for my talk.